Welcome back to the class, everyone. Today, in lecture 15, we dive deeply into the quantum mechanical mechanism that govern photoluminescence. In our previous lecture, we defined luminescence as the emission of light following energy absorption. Today, we will clearly distinguish between the two primary forms of photoluminescence, that is fluorescence and phosphorescence. Fluorescence spectroscopy measures the fluorescence properties of a substance. Physically, fluorescence occurs when emitted light possesses a wavelength equal to or longer than absorbed light. Because energy and wavelength are inversely related, the emitted photon always carries equal or lower energy than excitation photon. Phosphorescence spectrophotometry measures a fundamentally different delayed emission process. In phosphorescence, the emitted wavelength is strictly longer than absorbed wavelength. To understand why this emission is always red-shifted and dramatically slower, we must examine electron spin states. To understand emission pathways, we apply Pauli's exclusion principle to molecular orbits. Let us examine electron spin configurations. In the ground electronic state, electron spins are paired. One spin points up and the other down. Their angular momenta cancel. A state with fully paired spins is called a singlet state. Now consider excitation. When a molecule absorbs a photon, an electron is promoted to a higher orbital. If the electron retains its original spin orientation, the spins remains paired. This produces an excited singlet state. However, if the electron spin flips, the spin becomes parallel and unpaired. The molecule then occupies the excited triplet state. This distinction between singlet and triplet states controls the entire emission behavior. In a singlet state, spin remains paired. In triplet states, spin are parallel and unpaired. According to the Hund's rule, the triplet state lies at slightly lower energy than the excited singlet state. This energy difference is extremely important. Quantum mechanical selection rules govern transition probabilities. Transition involving spin change are considered forbidden. Therefore, singlet to singlet transitions are allowed, while triplet to singlet transitions are weak and improbable. This directly determines lifetimes. Excited singlet states decay rapidly, typically around 10 to -8 seconds. Triplet states persist much longer, from 10 to -4 seconds up to several seconds. Direct excitation from ground singlet state to triplet state is also forbidden, which is why such absorption is extremely weak experimentally. We visualize these processes using an energy level diagram called as a Jablonski diagram. At the bottom lies the ground state, denoted as S0. Most molecules exist here at room temperature. Above it lie excited singlet state S1 and S2. Slightly above S1 appears the excited triplet state, that is T1. Each electronic level contains many vibrational sublevels. Absorption transitions promote molecules from S0 to vibrational levels within S1 or S2. Direct excitation to T1 is rarely observed because spin change is forbidden. After excitation, molecules rapidly undergo vibrational relaxation. losing excess energy before emission occurs. To master luminescence, you must remember the characteristic time scales. Photon absorption is nearly instantaneous, occurring within 10 to minus 14 to 10 to the minus 15 seconds. Fluorescence emission occurs later, typically between 10 to minus 5 and 10 to the minus 10 seconds. Whereas phosphorescence is dramatically slower, its emission ranges from 10 to minus 4 seconds up to 10 seconds or more. Excited molecules relax through competing pathways. Radiative processes emit photons. These are shown as the straight arrows. Radiationless processes release energy as a heat and appear as a wavy arrows in the graph. The dominant pathway is simply the fastest one. If non-radiative decay dominates, fluorescence intensity decreases. Let us now interpret the complete Jablonski diagram. Thick horizontal lines represents electronic states S0, S1 and S2 and T1. Thin line indicates vibrational levels. Upward arrow represents absorption following excitation. Vibrational relaxation rapidly occurs, bringing the molecule to the lowest vibrational level. If emission occurs from S1 to S0, we observe fluorescence. Notice the emission arrow is shorter than the absorption arrow. This guarantees a longer emitted wavelength. If the molecule crosses into the triplet state T1, the delayed emission back to S0 produces phosphorescence. Now we define processes that reduce luminescence efficiency. First is vibrational relaxation. Excited molecules collide with surrounding solvent molecules. These collisions dissipate energy extremely rapidly, about 10 to the minus 12 seconds. As a result, fluorescence almost always originates from lowest vibrational level of the excited state. This energy loss produces the Stokes shift, where fluorescence appears at longer wavelengths than absorption. Next is internal conversion. This is non-radiative transition between electronic states of the same multiplicity, for example S2 to S1 or S1 to S0. External conversion occurs when energy transfers to the surrounding molecules without photon emission. Changes in solvent, temperature or viscosity directly affect fluorescence intensity, revealing these processes experimentally. The final mechanism is intersystem crossing. This is a non-radiative transition between states of different spin multiplicity, most commonly from excited singlet S1 to triplet T1. This crossing becomes probable when vibrational energy levels overlap. Phosphorescence occurs only after this transition populates the triplet state. Because the return from triplet to singlet state is a spin forbidden, the emission probability is low and the lifetime becomes long. Therefore, phosphorescence can continue from millisecond to several seconds, even after the excitation source is switched off. Thank you.